Hi, I'm Gary, and I want to show you how I use Cloudy. We've been talking about electron temperature, gas kinetic temperature off and on. Let's start thinking about the equilibrium that establishes what that temperature is. In video 25, we showed that in varying the ionization parameter, the radiation field went up and down by many, many orders of magnitude. But the temperature of the gas, the kinetic temperature, didn't change much at all. That's surprising because you would guess that you make the light really bright, the gas would get hotter. It didn't. So what does determine the temperature? And in turn, what determines the spectrum? So we're talking about photoionization equilibrium. Collisionalization is fundamentally different because in that general case, in collision ionization equilibrium, you'd actually set the temperature. So Cloudy has a coronal equilibrium command. We're thinking about photoionization. We're particularly thinking about photoionization of hydrogen because that's the most abundant element, and photoionization of hydrogen is a very, very powerful heating source for the gas. This is the equation for photoionization equilibrium taken from this old review article. So one way is you have to parameterize the radiation field coming in, and there's a phi of h command in Cloudy that says the intensity case that we've been talking about. So phi of h is the flux of ionizing photons given by this equation. So the terms here are the 4 pi j is the mean intensity. You divide by photon energy. This ratio is the flux of photons, and it's integrated over all energy. So this is the total number of ionizing photons. This is one of Cloudy's intensity cases. You have to multiply that by a cross section to get the photoionization rate. So this term here is the photoionization rate. And for the cross section, we've written it as a mean cross section because this J, there's actually a shape here, the SED shape. And just for purposes of this illustration, you want to collapse it into the integral of them all. So we have to get the right mean photoionization cross section. We don't do this in practice. This is just to do a simple analytical problem. That's the photoionization rate, the number of photoionizations per cubic centimeter per photoionization per second. Keep the units right. Dimensional analysis will save you in this. And you balance that with the recombination rate. And so the recombination has a recombination rate coefficient and a density. So you end up with a balanced equation like this, with the term on the left, the photoionization rate, ergs cubic photoionizations per cubic centimeters per second. And if it's time steady, if it's in steady state, that's equal to the recombinations. The recombination rate coefficient is recombinations cubic centimeter per second. And you multiply that by the density of electrons and the density of the ions, you get the recombination rate per unit volume. So a recombination means that the free electron finds a mate, loses energy, and they become bound. So that for hydrogen, an important recombination process is called radiative recombination. So the electron approaches the proton, is accelerated towards the proton. Accelerated charges radiate. If it loses enough energy by radiation, it can become captured and become a hydrogen atom again. So you start with an atom, photoionize it, start with an ion, recombine it to cycle. So this goes through to figure out the level of ionization, and this inspires this ionization parameter that's kind of built into Cloudy's view of how to do these problems. Now, what we want to do is set the temperature of the gas. So what we're going to do is we're going to talk about the heating going into the gas, the energy gains, frequently a capital G, and we're going to balance that with the energy losses from the gas. Heating equals cooling. So the temperature that's how the temperature will be set. So the gains, the energy per cubic centimeter per second, is number of atoms times the photoionization rate. So this term here is the photoionization rate at a particular frequency. And then you need to figure out the energy of the photoelectron, because that's the heat going into the gas. So if you have a 20 eV photon, if H nu is 20 eV, hydrogen has an ionization potential of 13.6 eV. So each photoionization deposits 6.4 eV of energy. So you integrate this overall ionizing radiation. So that's the total heat going in. So taking this form of the equation, you can uh, collapse it a little bit like that, and then you recognize the term from the phi to the n in the cross section. That's just equal to these terms in recombination rate because photoionization equals recombination. So the heating is density squared recombination coefficient times this mean photon energy. You're going to balance that with the cooling. So cooling is anything that takes the thermal energy of the electrons, converts it into light, which then escapes. So we've had a rough cooling function that we've been looking at in the previous couple of videos. What I did now is take that same input deck and made the temperature step really tiny, zero point 0.1 decs, to make a far smoother cooling function. So this is the way you would normally see this in a paper is a cooling function as a rate coefficient, ergs cubic centimeters per second. In that case, it's called a capital lambda. So it's the cooling function. The way cloudy works is that, the cooling is mostly the hundreds of thousands of lines with electron impact excitation, and there's some continuum processes too. So cloudy computes that every step of the way by summing up over the lines. It doesn't use a pre-computed cooling function, but this gives a concept of what we're doing. So the total cooling, which is what you would balance with the photoelectric heating, call this loss L. That's the this density squared times this capital lambda. So the way lambda is normalized, you multiply by the hydrogen density, total hydrogen density, and then by an electron density to get the cooling. So then the energy balance equation is cooling equals heating. Cooling was this term. Heating was G, this term. And these two are equal. Gains equals losses. Heating equals cooling. You see immediately that the densities are going to cancel out. Uh, so this cancels out, and you end up with this equation, which depends only on, well, slight dependence on temperature through the recombination coefficient. It, re it depends on the SED shape of the ionizing radiation. That's critical. And it depends on the cooling function, how the ability of the gas to cool itself. So it has no explicit density dependence, and it has no explicit dependence on the flux of photons. So it's a little bit paradoxical. So it's some atomic physics, the shape of the SED and the cooling function determine the temperature of a photoionized gas. So the next couple of videos, we're going to carry that forward and start thinking about what thermal equilibrium does to the observed spectrum. See you then.